Today we're going to take a look at polynomials and factoring polynomials through a variety of different methods. Difference of two squares, perfect square trinomials, sum difference of cubes. We'll later on get into quadratic and form, how we can factor with that method as well. So what is factoring? Factors are the numbers, the variables that multiply together to make a product. And it's the process of writing algebraic expressions. The product of those numbers are algebraic expressions. We have prime factors and composite factors. Prime numbers, we know, are numbers where the only factors are 1 in itself. Composite numbers are numbers that are not prime. When we refer to a polynomial being prime, we refer to that meaning it cannot be factored. It's as simplified as it gets. So we're going to run through a couple different examples here. Just first, talk about this acronym GCF. It means greatest common factor. And that would mean we look at all of the terms in a polynomial and we see what coefficients and constant common factors can come out. And also in the variables, we look and see if there are any common variable factors that can come out. And in this first example here with number 1, we won't run through all of these, but I'll give you guys a chance to get some practice on some of them. But on this first one, number 1, as a 2 and a 6 and a 6, I have a GCF, greatest common factor, of a 2. And that would mean when I factor something, I'm going to change the way it looks form-wise. This is an expanded form right now. And I'm going to put it into factored form, which means we're going to end up with parentheses indicating multiplication. And when you factor in a GCF is taking each of these terms, the 2x squared, the 6x, and the 6, and we're going to divide out the 2 and see what's left over. So if we divide out a GCF, we put it out in front, and what's left over will be inside some sort of a grouping symbol. In this case, we're going to use a parentheses. So if I divide out a 2 out of 2x squared, that means I have an x squared left over. If I divide a 2 out of 6x, I have a positive 3x left over. If I divide a 2 out of the 6, I have a positive 3. And then I'm going to look at the trinomial of x squared plus 3x plus 3 and see if that might be able to be factored. And if it does factor, I will continue until I get all the way down to simplified terms. And if not, I'm going to leave it alone. And in this case, that's as far as we can go for the factoring. All right, we look over at the second problem. And now I don't have any common integer factors or coefficient factors, but I do have a common variable factor. And if I look at the degree, the power of each of these, I have a 4th degree power, a 3rd degree power, and a 2nd degree power. And when you're dealing with factoring out exponents, you want to make sure the bases are the same. They're all x's, so that's good. And then we pull out the smallest common exponent, which means we're going to pull an x squared out of this. We're going to factor out an x squared. And again, leaving my grouping symbols, what's left over? If I divide a 5x to the 4th by an x squared, we learned with exponents, when you have common bases and you're dividing an exponent, so when you take an x to the 4th divided by an x squared, that's the same thing as saying x to the 4 minus 2, which gives us x squared. So we're going to get a 5x squared. Dividing an x squared out of 11x cubed gives me an 11x. And dividing an x squared out of negative 6x squared just gives me a negative 6. All right, now we're going to take a peek and see if maybe we can reduce or factor 5x squared plus 11x minus 6. One quick way you can tell is you look at the coefficient and the constant, and if I multiply them together, I get a negative 30. And if I think about the factors of negative 30, is there a way for me to use the factors of negative 30 to help me get an 11? Or factors of negative 30, we have a 30 and a negative 1, or negative 30, positive 1. We have a 2 and negative 15, or a negative 2, positive 15. We have a 3 and a negative 10, or a negative 3 and a 10. A 5, negative 6, or a negative 5, positive 6. And none of those can help me come up with this 11 in the middle, so I'm not able to factor this any further. So we would be done with this x squared, 5x squared plus 11x minus 6. All right, moving on. Number 3, a little different in the sense that now I have both coefficients and variables that I can factor out as a GCF. So GCF-wise, variable coefficients of 3. Each of these terms has at least x and at least a y in it. So my GCF is 3xy. What am I left with? Well, when you divide a 3xy by itself, you end up with a 1. And if I divide a 6x squared y squared divided by 3, I end up with a negative 2xy. And if I divide a 3xy cubed by a 3xy, I'm going to end up with a negative y squared. Once again, we're done there. All right. We're going to move on to some other factoring GCFs. They look a little different now. Now we've got, in some cases, a binomial that's a common factor. In other cases, we have this expression here in number 5. It's 2y is a common factor. So they can be a group of terms. They don't have to be a single term. But it's still the same process. If I look at 2y and 2y, they are both factors each of 3y times 2y and 2 times 2y. So I think of them, here we can do this, we can do a little substitution to maybe see how this works. Let's let u equal 2y. And then if I were to do that, I would have rewritten this problem as 3y times u plus 2 times u. And then now I can recognize that I have a common factor of u, and that u comes out. And I'm left with a 3y plus a 2. Well, now let's just resubstitute what u is. We said that u was equal to 2y, so now we just take that 2y out here. And we have 3y plus 2. You don't have to do the substitution, but that just might be a way of, instead of writing it as a multi-term expression, writing it as a single variable. Maybe that's easier for you to see what the GCF is. Right, when it's a binomial, it's the same concept. So I'm looking at the 4 and the negative x on problem number 6. But I see that both of these have an x minus 5 binomial part that is common. And so that x minus 5 binomial becomes my GCF. So bring it out. And when you have a binomial as a GCF, let's put that in parentheses. Otherwise, I'll show you what happens if you don't put that in parentheses. And then here's our grouping symbol for what's left over. And so if I pull an x minus 5 out of a 4 times x minus 5, I have just 4 left over. And if I pull an x minus 5 out of a negative x times x minus 5, I have just negative x left over. And that would be my answer. Now, if I had not put a parenthesis around x minus 5 and then done this problem, well, now we actually have something that's a little different. Here, in this problem, I have 2 factors, x minus 5 and a 4 minus x. If I forgot to do a parenthesis around the binomial x minus 5, I have now an expression that has x minus 5 times 4 minus x, which is meaning that would have been distributing, and then negative 5 would have been just a GCF, but that's not the case. So we don't want to do this. We want to make sure that we always pull out binomials and put them as a parenthesis or a grouped item when we're talking about a GCF. All right, and then again, once again, with 7 and 8, I'll let you guys work that out, but my answer answers would be the following: 2y plus 5 and 3y plus 2. And on number 8, I have an x minus a 3 common binomial. That means I have a 4 times an x minus a 3. I'm going to put a bracket here instead of a parenthesis. And then minus an x. I have a little more work to do on number 8. I'm just going to simplify what's in this bracket. If I distribute the 4, I get a 4x minus a 12 minus an x. And now combining my like terms, 4x minus x, I'm going to get final factored form. And I'll change this bracket to a parenthesis. It wouldn't matter if I left it as a parenthesis. 4x minus x is 3x minus 12. And then we would be done there. So in some cases, we're going to have some simplifying work still to do with the GCF. All right, expand it out a little further. Now I can have multiple binomials as a GCF. So in problem number 9, I'm looking here and I see I have 4 and then a 6, and then I've got this 2x plus 5 and 2x plus 5 squared occurring. And so again, I'm thinking about grouping, right? I'm thinking about looking at that big chunk and pulling out what's common. And then I have this big chunk and I'm pulling out what's common. So 2x plus 5, and then I have a 2x plus 5 squared. And we said earlier that when there's a common factor that has a power, we pull the smallest power out. So I know that a 2x plus 5 is going to come out of this, out of both of those. Let's go back and take a peek at our coefficients, because sometimes we just forget about those. So I have a 4 and a 6, and I know that a 2 is common factor of a 4 and a 6. And then we go look at the other binomial, and I've got a 3x plus a 1 squared and a 3x plus a 1, and that means at least 3x plus 1 can factor out of both of those. So now this group right here is what is outside of, okay, we're going to use the bracket. It's the GCF, and now I'm putting inside of the bracket what has been left over. So if I'm thinking about 4 times 2x plus 5 times quantity 3x plus 1 squared, and I take the 4 and divide a 2 out of it, that means there's going to be a 2 left over. 2x plus 5 divided by 2x plus 5, that means nothing's left over in terms of that binomial. And then a 3x plus 1 squared, and I pulled out a 3x plus 1, means there is a 3x plus 1 still left over. Working in the other bracket, the other group, the 2x plus 5 squared times 3x plus 1, doing the same thing. What's left over? So we pulled a 2 out of the 6. That means there's going to be a 3 left over. We pulled a 2x plus 5 out of a 2x plus 5 squared, meaning there's still a 2x plus 5 left over. And then the 3x plus 1 divided by itself, nothing else left over. So I can close off this bracket. So once again, that whole thing right there is the GCF that came out of those two brackets. Now I have some work to do on the inside with some distribution and combining like terms, so we'll continue to look at simplifying here. So GCF is still hanging out. And now on the inside, I got 6x plus 2 plus 6x plus 15. And then finally, we can write our final factored form here. I'm going to change those brackets back to parentheses. Again, that really doesn't matter. I have 6x and 6x combining like terms, and then 2 and 15. Get our factored form. So these are a little different. You just got to be thinking about binomials and finding out what's the same. I could have done the substitution thing here again like I did on the previous slide where I let, let's say, u equal 2x plus 5 and w equal 3x plus 1, and then factored out w's and u's and then reapply what those values are at the end here. So I'll let you work number 10. Here's what you're going to end up with, so you might want to pause. All right, it's kind of a long one today. So we're going to talk about our next way of taking factors, and that's by grouping. And usually we'll group when I have 4 terms. And I want to see if I can work with pairs. And I don't have to work with pairs where I always use the first 2 and the last 2. I could work with the first pair, the first term and the third term. I could work with the second and the fourth, the first and the fourth. But grouping just allows us to end up with a common, usually it's a binomial, but it doesn't have to be a common binomial after I group pairs together, and then that common binomial becomes my GCF. So, for example, if I look at 3x squared and the minus 6x group, and then I go over here and I look at the 4x and the minus 8 group, out of the 3x squared minus 6x group, I could pull a GCF of 3x out and be left with an x minus 2. Out of the 4x minus 8 group, I could pull a 4 out and be left with an x minus 2. Well, now I have a common GCF for both of these of x minus 2. And that then comes out as my GCF. And what's left over is the other remaining part. And I get the same answer I was getting with the previous groups. So grouping really just adds a step. We pair, and then hopefully end up with the same binomial, and that binomial comes out as a GCF value. We're gonna see what we can do here with a different grouping and see how I can pair different parts. So example number 4, let's say I look at part 1 and 3 of this 4-term expression, and I recognize that they both have at least a y in common, right? So they have a y in common. Means if I pulled out from those 2 a y, I'd be left with a w minus a 2x. Well, let's go take it the other 2 and look what they have in common, and they have a z as a common factor. And so if I pulled a z out of that, I'd be left with a w minus a 2x. Well, that's nice. I end up with a common binomial of w minus 2x, which means that is my GCF. So, final answer, w minus 2x, again, putting in parentheses, and a y plus a z. And there's my factoring using grouping. Again, I'll let you tackle these other problems here. Moving on, double barreling. This is just when I use 2 sets of parentheses. I'm going to show you some trial and error methods for how you can do these problems, and then I'll also introduce you to another method. It has a bunch of different names, and some people call it borrow from the clouds or Xbox, but let's see how this works. So our first one the x squared plus 5x plus 6. We're gonna end up with something that looks like this. And then how do we decide what goes where? Well, you guys have probably heard of the acronym FOIL. FOIL means to factor the first, the outsides, and the insides, and the last. This is when I'm starting with a problem that is double-barreled, and I'm ending up in that form. So we're kind of going backwards from what we're doing. Foiling takes us to the expanded form. And if I think about reverse foiling, I'm thinking about what are the factors of an x squared, where there's a coefficient right here, there's a coefficient of 1 right there. Kind of hard to see the green, let's change that. So there's a coefficient of 1 in front of the x squared, and the only factors of x squared are going to be x and x. Then I go and I look at the last term. And I think about the factors of 2 and 6. Well, I have 1 and 5, and I have, 1 and 6, and I have 2 and 3. What I want to do is end up with a 5 in the middle. And so I look at those factors, 1, 6, 2, and 3, and how would I add them together to give me a 5? And it would be that pair right there, 2 and 3. And so that's what's going to go on the last positions, 2 and 3. And then what goes in the middle are our signs. Now, since both of those are positive, that means these are both positive as well. If I were to now check it through foiling, I get x times x, x squared, x times 3, 3x, 2 times x, 2x, 3x, 2x gives me 5x, and then 2 and 3 gives me 6. So that's kind of a reverse FOIL, just using the factors of the first term and the last term, seeing how they work together to produce this middle number. All right, let me introduce you to another way of dealing with this. We'll do this with problem number 2. And kind of an unconventional method a little bit, but you'll see how it can be helpful when you have coefficients other than 1 in front of your x squared term. And I refer to it as an x box. And I'm going to move this guy out of the way for a second, slide it down. All right. So what do I do when I'm doing this next method called an x box? Well, there's a couple different parts. We have leading coefficient, middle coefficient, and c. This is just in standard form for a quadratic, ax squared bx and c. And when I set up this x box method, again, it has other names, but what I do is I'm going to put some numbers in these different positions here. So the very first thing we do is we take the leading coefficient and the variable, and we put that in this first position. And I know there's an x squared there, but we're just going to put a 2x. Then what we do next is we take the middle value, the b value, and that b value goes in the middle box. And then down in the bottom, we're going to take the product of 2 times negative 3, and that's what's going to go down here. All right, now what goes in on these side pieces? Well, we've got the factors of negative 6. That's what go into these side spots. We have the factors of negative 6. And here's what they are. We could have 1 and negative 6. We could have negative 1 and positive 6. We could have 2 and negative 3. We could have negative 2 and positive 3. And I'm looking for the group of factors that add up to, in this case, our b value, which is a 5. And add up to a 5, negative 1 plus 6. And so those factors go into these two positions, negative 1 and 6. All right, we're almost there. So how do I create my parenthesis from this? Well, I have 2x minus 1 as a parenthesis. And then I have 2x plus 6 as a parenthesis. And I know you're thinking 2x and 2x doesn't make 2x squared. It's just 4x squared. And you're right. So this is why it's a little unconventional. But watch what happens here. If I look at 2x plus 6, 2x plus 6, I could divide out a 2. And that would give me my final answer of 2x minus 1 times x plus 3. I don't factor out the 2 and put it out in front. I literally get rid of it. And there's my answer for 2x squared plus 5x minus 3. So that's a way that you can do factoring, this double barrel type method. Besides trial and error, that's another approach that you can do for factoring. All right, moving on here. What about the difference of two squares? Well, when I have a binomial, and it happens to be such that that binomial gives me a perfect square as the first term, and a perfect square as the second term, as in problem number 1, perfect square. Anytime I have a variable with an even power, that's a perfect square. And in 25, we know that's a perfect square. So there's a negative sign hanging out in between them, and that means we have a difference of two squares. So what do I do with the difference? Well, it goes into the double barrel form, but there's really not a lot of work I have to worry about here, because if x squared is produced by an x and an x, and 25 is produced by a 5 and a 5, now I just have to think about, well, how do I make this, what would have been a bx, a middle term, how do I make that go away? Well, the only way to make that go away is if one of those 5's is positive and one of them is negative. And so there I have x plus 5 times one of the x minus 5, giving me x squared minus 25. And again, check it, foil it, and see what you get. So a nice factoring tool. You've got to remember that it has to be a negative sign in between those. If it was an x squared plus 25, for example, I can't do this. This one would be referred to as a prime expression. I can't factor it. So you think x plus 5, but that would be a 10x in the middle after I foiled it. All right, let's keep on over here to 3. What do we do on 3? I look at 4. I see that's a perfect square. I have x squared. That's a perfect square. Negative 16. Everything seems to be working out so far. Perfect squares and a negative in between. But don't forget about this. Pull out my GCF. In this case, my GCF is a 4. So if I first factor out a 4, I get an x squared minus a 4. And that's all right, because an x squared minus a 4 is still a difference of two squares. And so then I have 4 times x minus 2 and 4, well, not 4 twice, but and then x plus 8. So you got to be careful sometimes with difference of two squares numbers that have a GCF. Let's always think about pulling GCFs out before we do any difference of two square work. All right, difference of two squares. I know we're moving kind of quick through here. And here's that note on a prime. X squared plus 25 is prime. Here's the example of why it didn't work. We got that 10x in the middle. So just be aware, can't have a positive sign in between. All right, then here's some more Xbox or factoring with double barrel. It's called a perfect square trinomial, and the reason it's called a perfect square trinomial is because it takes on this. If I had an expression of a minus b squared, for example, and I foiled this out, I get a squared minus 2ab plus b squared. And if it was a plus b quantity squared, I'd have a squared plus 2ab plus b squared. So what we have here in these examples are we have some expanded forms that are set up in one of those two ways right there. And we're trying to get to the factored form. So a quick check on this to how do I know if it's a perfect square trinomial. You look at the factors of the first and the last numbers. Factors of x for this problem number 1. I'm sorry, not factors. These are perfect squares. So I'm talking about the root of x squared, and the root of 9 is 3. And if I were to take 3 and x and multiply them together, and then double them, I would produce this middle term of 6x. And so I have, in this case, this perfect square trinomial. It doesn't factor any differently. I can still do my x box with these, or I can just trial and error. But what's unique about their answers is if I do factor them, x and x, and a 3 and a 3, it kind of looks like a difference of two squares, but the only difference is that these will become either plus plus or minus minus in these parentheses sets. Oops. So there we go. And another way of writing that, instead of writing it x plus 3 times quantity x plus 3, is we can write it as x plus 3 quantity squared. That's how we can do those. And so, not any different than what we've done before, just has a specific name given to it, a perfect square trinomial. We'll just do one more here. Let's take a look at one that has a negative in it. Let's go over here to number 6. And I'm looking at number 6. If I were to think about, I have an x squared, which is a factor, or a cube, excuse me, perfect square of x and x. 64, also a perfect square, 8 and 8. And y squared, also perfect square. But now I have this negative 16 in the middle. So if I had the 8y times x and I doubled it, I can get negative 16xy, as long as both of these are negative values. Negative times the negative makes the 64 a positive. So I could rewrite this as x minus 8y quantity squared. So perfect square trinomials. We're almost there. Hang in there. Perfect cubes. What are these guys? Well, instead of powers of 2, we now have powers of 3. And the rules here is just have to commit some of these things to memory, and this would be 2 of those items, is this rule for sum and difference of cubes. And you recognize them as being perfect cubes. They are binomials to start with, but now we don't have powers of 2, we now have powers of 3. And I'm going to end up in one of the 2 forms that's listed there under the rule. So as long as you can identify the terms of perfect cubes, and if there's a plus or a minus in between those 2 perfect cubes, you're going to have this to work with. So find out what your perfect cubes are, and those would become the a and the b values that we see in our rules here. Those guys are our perfect cubes of a cubed and b cubed. So in a generic sense, let's look at problem number 2. If I have these values written already as powers, this right now looks like a cubed plus b cubed, where the a is equal to my 3 and the b is equal to my y. And so if I just simply get in the habit of starting with the generic rule and plugging things in, so if I had a plus b, and then I have an a squared minus an ab plus a b squared, because that's what my rule says, right? Then I just plug in what a and b are. And that means I have a 3 and a y for a and b. And a 3 squared minus a 3 times a y plus a y squared. Well, that just leaves 3 plus y, 9 minus 3y plus y squared. And there's my final answer in terms of the factored form of this problem. So the rule is important. Now there is a little acronym that helps me remember how how the signs work, and that acronym is SOAP. And the S means same sign. The O is opposite sign. And then always positive. Well, what does that mean? Well, the same sign means if this is a plus to begin, if this one is a plus to begin with, if the binomial has a positive value in between your two terms, then that means the very first factored part of this rule will also be the same sign, in this case another plus sign. If that was a negative sign, you have a negative sign, right? Same sign. Then we have opposite signs. So the opposite sign says we're going to be the opposite of what we began with. If I began with a positive, I'm going to have a negative. And then always positive, this component, means that last term there in my factored form will always be a plus. So there's maybe a little reminder for you to how I set my signs up for this problem. So, all right, we're there. Our last one, a little mixed practice for these problems. So it's just going to be, got to take a look at our problems and think GCFs first, and then do I recognize any binomials that happens to be perfect squares or sums and differences of cubes? And if I have 4 terms, I might want to think about grouping. So there's a lot to think about when you're doing factoring. Let's take a look at this first one. We'll kind of work all 5 of these together. So I look at the first one. I have 2 terms, so I don't want to get on the whole bandwagon of difference of squares and sums and differences of cubes just because I see a power of 3 or just because I see 2 terms. What I do recognize, though, is that of an 18 and an 8 and an x and an x cubed, I have a 2x as a GCF. And that means I'm going to have a 9x squared minus a 4 left over. Don't get all excited, though, because you're not quite done. You have a difference of 2 squares. 9x squared, perfect square. 4, perfect square. There's a negative in between there. And so I can break that down even further. I would get 2x quantity 3x minus 2 times quantity 3x plus 2. Do these step by step. Then you become real comfortable with them. There's not a whole lot of work to show with factoring, but work them step by step. All right, I'm looking at this number 2 problem, and I see in the first, I always look at the first 2 and the second 2 as pairs and see what I can pull out if I end up with something that looks the same. And if I'm looking at 2xy and negative 6x, I can pull a 2x out, and I'd be left with a y minus a 3. All right, so let's go over here to the next one. Look at those 2 pairs, and if I pull a 3w squared out, I'd be left with a 3 minus a y. Well, let's see what happens. 3w squared comes out of this group, 3 minus y left over. 2x comes out of the blue group, and a y minus the 3 left over. Well, this is a unique situation here because I see I have a y minus 3 and a 3 minus y. And they have the same numbers, one's opposite, one's of the other, and the y values, one is opposite. So what I've got here is a situation where we have an opposite. So let's take a look at the opposites. A y minus a 3. How is it compared to a 3 minus a y? Right? Are these equal? That's the question. And they look close, but they're not quite there. And the difference is their signs are all switched. In this first one, I have a positive y and a negative 3. In this second one, I have a negative y and a positive 3. So what I want to do in this case, when I see these, are called opposites. And when I have opposites, I factor out a negative 1. So, what does that look like? Here, let me make some room up here. If I took a y minus 3, and I pulled out of that a negative 1, I'd be left with a negative y plus a 3. And a negative y plus a 3 is the same thing if I just rearrange the order as having a negative 1, 3 minus y. And now I have the same looking binomial. And so what we do here is out of either the blue one or the red one, since I already had gone and taken care of the blue one, we'll go ahead and leave it that way. So let me move this problem number 4 down a little bit. So out of the blue group, we're going to go ahead and pull out a negative 1 from this. So a negative comes out, the 2x is still there, and by pulling out the negative 1, and I'm going to, again, flip the order just so that they look the same, this would become now a 3 minus a y. And then I still have the 3w squared times 3 minus y. There's my common factors. And in grouping, we take those and we write them as our GCF. And what am I left with? A negative 2x and a positive 3w squared. And there we go. So we haven't seen the opposite yet. And again, I'm looking for the signs just reversed. And in the case of y minus 3 and 3 minus y, they were just the opposite of each other. So factor out that negative 1. Number 3, I have, let's see, a 2 as a common coefficient, and an x as a common variable for x's, and a y. That means I'm going to be left with a 2x squared minus an xy plus a y squared. And I'm looking at that 2x squared minus xy plus y squared, and thinking if I can factor that even further, and I'm not going to be able to do that, have this negative in the middle. Factors of 2x squared y squared, 2 and x can be positive or negatives, and it's not going to help me with that negative xy in the middle. So I'm done. Number 4, almost there, folks. Pull out the 2x, that's my GCF. X cubed minus an 8. All right, I have a binomial. That binomial is 2 terms, well, obviously 2 terms. One of them is a power of 3, which means it's a perfect cube. 8 also is a perfect cube. So what I have here is a difference of 2 cubes. Which means I'm going to have to break that thing down. And we go back and we take a peek at our rule. We say, take the cube root of x cubed, I get an x. Take the cube root of 8, and I get a 2. And then I'm going to be left with the x squared opposite sign of x and 2 multiplying together, and the square of 2, which gives me a 4. Now, it's real tempting to probably try and factor that last trinomial, but we can't. All right, and then our last one here. I have no GCFs that can come out. This is what we call quadratic in form, meaning it looks like ax squared bx and c. And one way to do these, and you can do this without substitution, but let me just show you the substitution. This, again, I'm going to let u equal y squared. Now, why did I do this? Well, first of all, I'm recognizing quadratic in form because I see that the powers, the middle power, is half of the leading power. And when that happens, for a trinomial set up like this, I that means this problem becomes 2u squared. Why did that happen? Let's look at this. A y squared squared is the same thing as a y to the fourth. And if we let u equal y squared, well then there we go. That's where my u squared comes from. All right, so let's keep going here. So we're going to let u equal y squared. That means I have u squared, 2u squared, minus 5u minus 12. And we're going to go ahead and factor this thing. 2u and u. I'm going to just do a trial and error method here. I want a negative 5 with the factors of a negative 12. That means if I did 2 times negative 4, I'd get negative 8. And negative 8 plus 3 would give me negative 5 in the middle, and it produces the negative 12. All right, so I have factored it using these u's. Now we're going to reapply our u as a y squared. Remember, we substituted. Now we're going to put back y squared. And I get 2y squared plus 3. And y squared minus 4. Look at that. We've got a difference of 2 squares down there. Y plus 2 and a y minus 2. And there we go. I could have done it without substitution as well. We could have just taken this quadratic and gone right into, I could do Xbox with this thing as well. So I have a 2y squared and a y squared. And I'm still thinking, how do I make a negative 5 out of it? So I'd still use the same pieces here. The negative 4 and the positive 3. And there we see again the same result that we had when we did substitution. Right? These are equal to each other.